Hello everyone, today we are starting chapter 3, which is about probability. We will only see the basics of probability. We will use those concepts later on in discrete distributions. So here's a review activity which you can do at your own time. We actually did some activity like this, so I'll skip that one. So here are some important terms. First of all, what's a random experiment? A random experiment is something where the outcome is uncertain, so you do not know the answer. Like for example, when you throw a coin, it can be heads or tails, so it's a random experiment. And basic outcome is a possible outcome of a random experiment. And sample space is the collection of all possible outcomes. And event can be any subset of the basic outcomes from that sample space. So we know the intersection. What's A intersect B? So this is A here, and this is B here. A intersect B is the set of all outcomes in S that belong to both A and B. Now, two events are mutually exclusive. So here we have A, the event A, here event B, but they have nothing in common, nothing. So the intersection A intersect B is empty. If the intersection is empty, then this is called mutually exclusive events. Now, union. A union B. That means either A or B has happened. Or it can be both. Now, this is A, this is B, and this area is, for example, here. This is A intersect B, but we are looking for A union B, so that will be like all the A and all the B. So A and B all together will give us the A union B. Now, events are collectively exhaustive if the union of those events are equal to sample space. So for example, when you toss a coin, it could be head or tail. So we have two outcomes, and we don't have a third outcome. So these two outcomes will be collectively exhaustive. So if the events completely cover the sample space, this is called collectively exhaustive. Now the complement is the opposite of the event. So for example, the complement of event A is the set of all basic outcomes in the sample space that do not belong to A. So for example, here we have A. And anything inside will be A. But if you're looking for the complement, then it will be anything outside. So this area, anything that doesn't belong to A will be A complement. Sample space, here's an example. We are rolling a dice. And if you are rolling a dice, we know that we can have 1, we can have 2, 3, 4, 5, or 6. So in that case, our sample space will be any of those events. So it's the number from 1 to 6. So let A be the event that number is rolled even. So what are the even numbers here? We have 2, 4, and 6. So I'll take those numbers. 2 will here, 4 belongs to here, and 6 belongs to here. So this will be event A. Now let's say we have event B. The number is rolled at least 4. So it could be 4, 5, or 6. So it could be 4, 5, or 6. So that will be event B. Now, we defined event A, the even numbers from 2, 4, 6. And we defined event B, any number that's higher than or equal to 4. That's 4, 5, 6. So the complement of A will be anything in the sample space that doesn't belong to A. So this could be 1, or 3, or 5. See, they have nothing in common between A complement and A. There's nothing in common. And the same thing is with B. Now B is 4, 5, 6. So what that means is B complement will be 1, 2, 3. So they have nothing in common with B. Now let's look at intersection. A intersect B. What exactly they have in common? So we have in A, we have 2, 4, and 6. In B, we have 4, 5, 6. Oh, they have a 4 here and 6 here. We also have a 4 here and 6 here. So those are the numbers that are in common. So 4 and 6. That will be the A intersect B. Now, if you want to look at A complement intersect B, is A complement is here, and A complement, this is A complement, and B is here, and I see only one number, which is like 5. Here I have number 5, and here I also have number 5. So that's what they have in common. So the common intersection is here. And the union. Union means they are together. So if you put them together, we will have 2, 4, 5, 6. And obviously, if you take a union of a complement with the event itself, that will give us the sample space. So let's look at some applications. Now, is A and B mutually exclusive? No. Why? Because they have something in common. They are not mutually exclusive because they have some numbers that are common to both, like 4 and 6. Now, are they collectively exhaustive? No, they are not, because we have some numbers here, like 1 and 3, and the union doesn't contain this number. Therefore, A union B are not collectively exhaustive. Now, what's probability? Probability is the chance that an event will occur. And for the event A, for example, the probability of that event is always between 0 and 1. It can be 0. If it is 0, that means impossible. It can be 1, that means it means certain. So the basic idea, the very fundamental thing that you should know about the probability, let's say P, that number is always between 1 and 0. And both of them are enclosed. If it is 0, that means impossible. If it is 1, that means certain. Now, we also need to know some things like combinations and permutations. A combination has a formula. It is C. This C means combination, and N is the big number, K is the small number. So, for example, it could be combination of N items taken K at a time, and that's equal to n factorial over k factorial times n minus k factorial. And when we say factorial, that means you multiply that number like n minus 5, n minus 2, until it reaches to 1, the multiplication, the last multiplication. And by definition, 0 factorial is equal to 1. That's the definition. And also 1 factorial. So you want to know about the 1 factorial. Let's make it blue here. So 0 factorial is equal to 1. 1 factorial is also equal to 1. So when you're taking combination, you are making a choice. And in that choice, the order is not important. For example, for this course, we will have a group project. In that group project, you will be, let's say, 5 students together. And it doesn't matter which student is chosen first or second, you will be in the same group. That's a combination. Now, similar concept is the permutation concept. In permutation, again, we are choosing, let's say, x objects from a total of n objects. And in this time, the order is important. So if the order is important, then we are using the permutation formula, p and x. And that's equal to n factorial over n minus x factorial. So in any case, when the order is important, you can also make combinations from the orders. So that's why a permutation is almost always higher than the number of combinations, or equal to. But most likely it will be higher. So in combinations, we are choosing x objects from n. So basically there's a relationship between combination and permutation. Once you find the permutation of x objects from n, permutation pxn, and if you divide it by, if you take the pxn and divide by the x factorial, that will give you the number of combinations. So for example, in permutations, you are dividing, let's do the permutation here. So n factorial divided by x factorial, that will give us the permutation p x n. And if you divide this by, actually sorry, that was a mistake. Sorry. Yes, no. N factorial over n minus x factorial. Yes, now this will give us p x n. Yes, and if you divide that number p x n with x factorial, that will give you the combination. So here's a class activity, and maybe we will do it later in the class. Now probability. Again, what are the probability postulates? For any event in a sample space, the probability is always between 0 and 1. If it is 0, that means impossible. If it is 1, that means certain. And if you sum up all the basic probabilities, basic outcome probabilities, that will give us the probability of any event. And the probability of the sample space is always equal to 1. So those are the basic definitions of probabilities. Now, let's say we have an event and we have the complement. So we have the event A and we have the complement A complement. Now, the probability of the complement is equal to 1 minus the probability of event A. So let's say if the event A has a probability of, let's say, 0.4, the probability of A complement will be 1 minus 0.4, which is 0.6. So in any case, the probability of the event plus the probability of the complement of that event will be equal to 1. Now, addition rule, the probability of the union. The probability of A union B is equal to, let's make it like blue, A union B. We have PA plus PB minus PA intersect B. Now you might be wondering why we have a minus here, A intersect B. Because this is common in both A and B. So if we do not subtract this number, we will be double counting it. We want to count the intersection only once. That's why we are subtracting the probability of the intersection. So this is a joint probability table. We have the event A and A complement here, event B and B complement here. Now, let's just make it, I'll make the intersections with, say, red color. Now, let's do something like this. Actually, just do like this, so that we can see intersections. Yes. Now, A intersect B. The probability of this event will be on this corner, P A intersect B. Now let's do it for the complements. A complement intersect B complement. This is probability of A complement intersect B complement. Now probability of A intersect B complement will be here. This is P A intersect B complement. And probability of A complement intersect B will be here. Probability of A complement intersect B. Now those are called the intersection probabilities. Now what about the probability of, let's say, B? Here, this number is the probability of B. What about the probability of A? Here on the right side, we have the probability of A, and this is the probability of B complement, and this is the probability of A complement. Now those are called the marginal probabilities. And finally, we have the probability of the sample space. Here, that probability will always be equal to 1. So the probability of the sample space is always equal to 1. And this is a joint probability table. Now we also have this concept called conditional probability. Conditional probability of the event means that you're looking for that probability given that something else has happened. So for example, this is probability of A, and this term here means given, this means given B. So A given B, probability of A given B equals P A intersect B over PB. So this is the conditional probability of event A given that B has happened. And here it is probability of B given A has happened. And this is probability of A intersect B over PA. So this line here means given. So probability of B given that A has happened. That's the idea of conditional probability. Now, two events are statistically independent if the probability of their intersection is equal to PA times PB. So events A and B are independent when the probability of one event is not affected by the other. So what that means is A doesn't impact B. In that case, the probability of A given that B has happened is the same as PA. Probability of B given that A happened is the same as PB. Now, this equation holds only if A and B are independent. So if they are independent, the conditional probability will be equal to the probability itself. And for multiple events, let's say E1, E2 up to EK, they are statistically independent if the joint probability is equal to the probability of the multiplications. Now here's an example. Let's say there's a car market, and we have some cars that have air conditioners. We have some cars that have CD players. We have some cars that have them both. We have some cars that doesn't have AC or CD. We have the probability distributions here. Are the events AC, air condition, and CD, compact displayer, statistically independent? Now, to be independent, we have to check the probabilities. The probability of AC intersect D is here. AC intersect CD, that is 0.2. Now, let's look at the probability of CD. Okay, that's actually AC and it's a straight stone. Let's make it orange. Probability of AC. Here we have AC, and that's equal to 0.7. Now let's look at probability of CD. That's equal to 0.4. And if you multiply those numbers, probability of AC times probability of CD, that's equal to 0.27. Now, that number is not equal to 0.2. So they are not really equal to each other. Now, if they were equal to each other, they will be independent. But here, they are not equal to each other. So these two events are not statistically independent. And that makes sense, because if a car has an air conditioner, it's likely to have a CD player. And we have a class activity, which we might do in the class later on. And the same concept for between two events. We can also apply this concept to multiple events. The logic will be the same. Probability of A intersect B is equal to the number of outcomes satisfying A and B over the total number of elementary outcomes. And it's also possible to compute the marginal probabilities. So for example, we have A and B. The probability of A will be equal to probability of A intersect B1, A intersect B2, multiply all the events intersecting A with total number of K mutually exclusive and collected exhaustive events. Now this is an interesting activity, but we will do it, we might do it later on in the class, or I will just let you do it yourself. So that's it for this week. So I hope to see you next week.